On slide 32, we turn to LTA with transition-specific distal outcome means, introducing the so-called dot language. So if you look at this picture again, that we used for a multi-step LTA, where we have the measurement part up here, distal outcomes out here, and covariates down here. Let's remind ourselves what this picture means. So it specifies that C2 influences Y. C2 influences the Y, the distal outcomes, and they're not influenced by C1. So to handle that, we used Y parameters that we mentioned in the model C2 classes to let them vary across the C2 classes. And that specification then implies that the Y parameters are held equal across the C1 classes. So when we say that they vary across C2 classes, we implicitly also say that they're held equal across C1 classes. Otherwise, they would be influenced by C1 as well. Now, Y parameters not mentioned in model C1 or model C2 classes implies that the means and thresholds for the distal outcomes Y vary across all combinations of the C1, C2 classes by default. So what if you wanted something in between of those two extremes? Well, let's look at slide 34. We introduced the dot language, and in this case we want a distal mean or a threshold specific to one specific LTA transition. Now the Y parameters then mentioned in model C2 and in a specific class combination, which corresponds to a certain transition pattern, can be specified using the dot language. So for instance here, C1 class number 2 dot C2 class number 3 can have a specific distal outcome mean or threshold. A certain transition pattern that we're interested in, and to see if that has a special effect on the distal outcomes. And that dot specification overrides the Y parameter equalities across the C1 classes that was implied by specifying that they vary across model C2 classes. And syntax for that is as follows. The dot specification can be placed in the overall subsection of the model or below the model C2 under a new model command section. We're going to take the first alternative here. So slide 35 then, let's take a look at how two-step analysis deals with this. So we have the stage A analysis here using two-step, where the used variable list is like this, including the indicators. And we do data imputation just like before. And nothing is new on this slide so far. What's new comes on slide 36, where in addition to this overall statement, we also add a class combination specific statement. So let the transition from class 2 to class 3 have a specific distal mean and threshold. C1 sharp 2 dot C2 sharp 3. And then we give in brackets those intercepts or means and thresholds. So that's how you do this specific transition pattern influence on the distals. And then the rest is just standard two-step. We fix the measurement parameters here on slide 36 and continue on slide 37, where as before we have the effect of model C2, effect of C2 on the distals in each of the classes. But we also allow on slide 36, going back one, to have a specific effect from this transition. So no longer are the thresholds and means the same across all of the C1 classes, as an effect from C2 would imply, but we let the second class of C2 in combination with the third class of C1. Did I say that right? The second class of C1 in combination with the third class of C2, let that have a specific threshold mean. So no longer equal to, in this case, specifically the other C1 classes. All right, so then we take one step further on this dot topic. Slide 38. What if we want distal means and threshold specific to all LTA transitions? Well, we can draw it like this. So the influence of C2 on the distals, I brought the distals down from up here to down below here for the simplicity of the figure. And we're saying that the influence of C2 on the y's is also influenced by C1. So it's a C1, C2 interaction here with these broken arrows. Should be broken arrows everywhere. That, well, it should be broken arrows 1, 2, 3. There are 3 broken arrows, yes, and then the direct effect from C1 as well. Main effect, one can call it. Now in this case, we said that we could just not mention the distal outcome means and thresholds, and they would all be different across all the classes, all the class combinations. That's true, but we may want to explicitly say this for the following reason that I will make clear on the next slide. This is a new data set here with the distal outcomes. Y1 is continuous, Y2 binary, Y3 ordinal. I call it LTA distal N to K dot on slide 39. So we do 3-step here. We mix things up a little bit, varying the 3-step with 2-step and BCH. And we have done a previous run, and we want to do a reordering using S values, as you see bottom right here. And we have the op seed to do that. And no C2 on C1 in the first step as before. And we have measurement equalities across time, and we save the C probabilities in C prob dot dat data set. And off we go into the last step of 3-step using this dot language. So the file is cprob dot dat, and we have on the use variable list the most likely class memberships, C1 and C2 in the nominal variables, and you have C2 on C1. So the new interesting thing here is that you have the dot language specification here then for each combination, C1, so it's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And give the means, means and threshold for that. There are no covariates here, so there are means for the continuous. But we also can give the labels here. That's not necessary to do, but we want to give that here because probably you will be interested in looking at differences between different transitions, different rows here in terms of, say, the mean of Y1. Is the Y1 mean different between this transition as compared to this other transition? And to do that, you have to have parameter labels that you then use in the model constraint statement to create a difference between the two and estimate that difference and get a standard error automatically by the delta method for that to get a test of whether that difference is significant. And since it's 3-step, we also have to have the fixed logits in the input, as just like before.